Organic chemistry. It's the science of, well, life itself. And in this explainer, we're going to break it all down for you, piece by piece. Okay, let's be honest. When you hear organic chemistry, what comes to mind? For a lot of people, it sounds complicated. You picture these crazy diagrams, these super long names, and it can feel a little, intimidating.
But what if I told you that this whole gigantic field really just boils down to one single element and a handful of rules that are actually pretty easy to learn? Seriously.
And that's exactly what we're going to do. We're going to build a molecule right from the ground up. We'll start with that one key element and see how everything else just clicks into place. And yeah, we'll even figure out how they get those wild names.
All right, first up, let's meet our superstar, the ultimate builder of the molecular world. We're talking about carbon.
So why carbon? I mean, you've got this whole periodic table full of elements. What makes carbon so special that it's basically the backbone of all life?
Well, the answer is pretty amazing. It's because carbon is like the ultimate Lego brick of the universe. It can link up to form all sorts of shapes, long straight chains, chains that branch off, and even complete rings. This flexibility is why there are millions and millions of different organic compounds out there. So, what are carbon's superpowers? First, it loves to bond with other carbon atoms, making those stable chains and rings. Second, it's not limited to just one type of connection. It can form single, double, and triple bonds. And third, it's a social butterfly. It happily teams up with other elements like hydrogen, oxygen, and nitrogen. The variety is just incredible. Okay, so we know carbon can build these incredible structures, but how do we actually draw them? How do we take something that exists in 3D space and represent it on a flat screen? We need a kind of blueprint.
So let's start with a little puzzle. Look at these two compounds, butane and 2-methylpropane. Now check out their chemical formulas. Both are C4H10, 4 carbons, 10 hydrogens, identical. So, are they the same molecule? What do you think?
And the answer is nope, not at all. This is where a structural formula is absolutely crucial. See, it's not just about what parts you have, it's about how you put them together. Butane is a simple straight chain, but 2-methylpropane? It's got a branch, same parts, totally different molecule.
And there's a name for this, of course. It's called isomers. Think of them as molecular twins with different personalities. They have the exact same list of ingredients, the same molecular formula, but they're built differently, so they have different structural formulas.
And to really get a feel for what they look like, chemists use 3D models. The ball and stick model is awesome for seeing all the bonds and the angles between them, but the space filling model, that gives you a much better idea of the molecule's overall shape and size.
All right, with millions of these things could get messy really fast. So how do chemists keep it all organized? Well, they group them into families, and it's based on a really clever idea.
And that idea is the functional group. This is the game changer. Think of it as the molecule's action figure accessory. It's a specific atom or a group of atoms that you stick onto the carbon backbone, and it determines almost everything about how that molecule is going to act. It's what gives the molecule its chemical identity. Let me show you what I mean. Let's start with this super simple guy, ethane. Just 2 carbons, all surrounded by hydrogens. It's a basic no-frills alkane. Okay, now watch this. We're going to perform a tiny bit of molecular surgery. We'll take off one of those hydrogens and replace it with this OH group. That's our functional group. And poof, we don't have ethane anymore. We've just created a brand new substance, ethanol. And that one tiny change makes a huge difference. Ethane, it's a gas at room temperature. It won't react with sodium at all. But ethanol, our new molecule, it's a liquid, and it absolutely will react with sodium, bubbling away to release hydrogen gas. All because of that one little functional group. Incredible, right? So we've got millions of compounds, and we can group them into families, but we still need a way to give every single one a unique, universally understood name. And thankfully, there's a totally logical system for doing just that. The system is kind of like learning the language of chemistry. For the most basic family, the alkanes, it's a piece of cake. There's a prefix for the number of carbons, meth for 1, F for 2, prop for 3, and so on. You just stick the suffix ane on the end. So a chain with 6 carbons? You got it. It's hexane. Okay, that works great for straight lines. But what about the messy, branched molecules we saw earlier? Don't worry, the system's got that covered too.
We just need to add a few more steps to our recipe.
All right, deep breath, take a look at this thing. Your first thought might be, how in the world do you even begin to name that? It looks complicated, for sure. But it's really just a puzzle, and all we have to do is follow the rules.
And here are the rules. It's a simple 4-step process. Step 1, find the longest single chain of carbons. That gives you the last name, the root of the molecule. Step 2, number that chain, but you have to start from the end that's closest to the first branch. The goal is to use the lowest numbers possible. Step 3, identify all the little branches that are sticking off. And finally, step 4, just put all the pieces of the name together.
So, let's try it on our molecule. First, what's the longest continuous chain? If you count it out, it's 6 carbons long. So, the last name is hexane. Now, we number it. If we start from the left, the first branch is on carbon number 3. If we start from the right, hey, the first branch is on carbon number 2. 2 is lower than 3, so we have to number it from right to left. Easy.
And now for the grand finale. We have these little 1-carbon branches, called methyl groups, on carbons 2, 2, and 4. And we have a 2-carbon branch, an ethyl group, on carbon 3. Now we put them in alphabetical order, so ethyl comes before methyl, and we get 3-ethyl-2,2,4-trimethylhexane. It looks like a mouthful, but every single part of that name is a precise instruction. It's a perfect blueprint in words.
And there you have it. We went from the special properties of one little atom, carbon, to these things called functional groups that give molecules their character, all the way to a beautifully logical system that lets us name an almost infinite variety of structures.
So you see, organic chemistry isn't just about memorizing facts. It's a system, a logic, a language for describing the very stuff that makes up our world. Now that you know the rules, what molecules will you be able to recognize and decode? Thanks for watching this explainer.